All right, so let's talk about 3.4. 3.4 is about linear and angular speed. So this is another application of radian measure. So first of all, linear speed is an object, or sorry, the linear speed of an object is a measure of how fast the position of the object is changing, and we can calculate the linear speed. We usually use v for velocity, but v is s over t, where s is the distance through which you've traveled, and t is the amount of time that it took for you to do so. So, you know, if you go 60 miles in 1 hour, then your velocity is 60 miles per hour. If you go 30 miles in 15 minutes, then your velocity would be, well, 15 times 4 is 60, that's 1 hour, right? So 30 times 120 miles per hour, which is really fast, right? So if you go 30 miles in 15 minutes, then you've got, anyway, but that's the idea, right? So that's how we measure velocity. So note that when the object is moving in a circular path, then s is an arc length, right? And that arc length, we've discovered, is the same thing as the radius times the angle through which the particle moved, or the object moved, right? So s equals r times theta. So referring to this picture here, the angular speed of an object, so the speed at which theta is changing, I guess, right? The angular speed is a measure of how fast the angle theta is changing, and we can find it. So first of all, the symbol that we use is this Greek letter omega. This is a lowercase omega. So we say omega is theta over t, where t is the amount of time that it takes for an object to move through an angle of theta radians. Okay. So linear speed here, v equals s over t. Angular speed, omega equals theta over t. Right? It's how fast the angle is changing. So now here's the relationship between the two, right? If v is the linear speed of an object and omega is its angular speed, then v equals r times omega. That should make some intuitive sense, right? It's the speed at which the angle is changing times the radius of the circular path that it's on, right? But we can prove it. We can say, you know, v is s over t. S is the same thing as r times theta, right? Arc length is radius times the angle. So s over t is r theta over t. We can move the r out, and then theta over t is just omega. So this is just r times omega. Okay, let me give you some examples of this. So example 1 here says, the human wrist can rotate through pi over 2 radians, so it's 90 degrees, in about 0.45 seconds while holding a tennis racket. If the distance from the tip of the tennis racket to the wrist joint is 2 feet, calculate the angular speed of the human wrist swinging a tennis racket and then the linear speed at which the tip of the racket is moving. So for part A, the angular speed, omega, is theta over t. So it's the angle through which the object is traveling divided by the amount of time it takes to do so. This one says that the human wrist can rotate through pi over 2 radians in 0.045 seconds. So let's see about how much that is. We'll round to, I guess, 3 sig figs. So let's see. Pi over 2 divided by 0.045. So that's about 34.9 radians per second. Okay, so that's it for part A, right? That's the angular speed, 34.9 radians per second. Okay, part B asks us for the linear speed. Okay, well, the linear speed v, we just discovered v is r times omega, right? And we just figured out what omega is. We did that in part A. That was a really bad omega. I need to practice drawing omegas. Anyway, but V is r times omega. What is r? R is the radius of the circle. That's given to us here, right? It's the distance from the tip of the tennis racket to the wrist joint, right? Because it's your wrist that's moving this quickly. So anyway, the radius is 2 feet. So this is 2 feet times 34.9 radians per second. Okay, so we just multiply by 2. That comes out to about 69.8. So 69.8 feet per second. Okay, and that's that. I wonder what that is in miles per hour. So how many miles per hour is that? Well, so you could do some, I don't know, let's do it. 69.8, just because I'm curious. Feet per second. Oh, but I'd have to know how many feet are in a mile. I think it's 5,280 feet in 1 mile. Could be wrong. But then seconds, there are 60 seconds in 1 minute, and then 60 minutes in 1 hour. So we're going to divide by 5,280, but then multiply by 60, and then multiply again by 60. So let's see. 69.8 divided by 5,280 times 60 times 60. That's 47.6-ish miles per hour. Right, because the feet cancel, the seconds cancel, the minutes cancel. We're left with miles per hour. Yeah, so 47.6 miles per hour. That's pretty fast. Okay, moving on. By the way, you could have left that last answer in feet per second. That would have been fine. It's just my brain thinks better in miles per hour, so I just wanted to get a sense for how fast that was. Anyway, number 2. Suppose that point P is on a circle with radius 10 centimeters and ray OP is rotating with angular speed pi over 18 radians per second. Find the angle generated by P in 6 seconds. Okay, so in other words, maybe P starts here, so we'll call this P0, right? Its starting location. And then O, P is on a circle, ray OP is rotating with it. Okay, so we'll say O is here at the center of the circle, and this ray OP is rotating with a speed of 18 over pi radians per second. So it's going to rotate a certain amount, and I really have no idea how much it's going to rotate, but it's going to rotate through some amount, and we want to know what this angle is. We'll call it theta. Okay. Okay. So let's see if we can do this. We know that the angular speed is pi over 18 radians per second, and we know that it's going to travel for 6 seconds. So I'm going to manipulate this equation. Omega is theta over t. And I'm going to say we're looking for theta, right? So theta is going to be omega times t. That's omega, we said, was pi over 18. And t, we said, was 6 seconds. Oh, so that's easy, right? That's pi over 3. Okay, so there you go. There's omega. Or sorry, there's theta. There's theta. So theta goes through a rotation of pi over 3 radians. Okay, now part B says, find the distance traveled by P in 6 seconds. The distance traveled by P. So in other words, we're looking for S, right? We're looking for this arc length. So I'm gonna say I'm trying to think of the easiest way to do this. I could sit here and stumble around, or I could just think for a little bit. So find the distance traveled by p. We're looking for the arc length. So s is just r times theta. And we just found theta in the previous step, right? Okay. And the radius we know. The radius is 10 centimeters. Okay? So this is 10 centimeters times pi over 3 radians. Okay, so that's 10 pi over 3 centimeters, which is approximately how much? Let's see. 10 pi over 3. That's about 10.5. Okay, so about 10.5 centimeters. Okay, and then part C. Find the linear speed of p in centimeters per second. Well, the linear speed is r times omega. So that would be 10 times omega is the angular speed. That's 18. That's pi over 18, right? So it's 10 times pi over 18. Which of course that's 5 pi over 9, but it's approximately 1.75. This was centimeters, so this must be in centimeters per second. Okay, there's more than one way to skin a cat on these problems though, right? So if you found a different way to do it, as long as you're ending up at the same place, chances are it's correct, right? Okay, so that's that. Number 3 says a belt runs a pulley of 6 centimeters at 80 revolutions per minute. Part A says find the angular speed of the pulley in radians per second. Well, we know that it rotates at a rate of 80 revolutions per minute. We need to change revolutions per minute into radians per second. So the angular speed is 80 revolutions per minute. But we want to get rid of revolutions. Oh, we want to get rid of revolutions and keep radians. So the question is, how many radians are in one revolution? Well, there are 2 pi radians in one revolution. Okay, so that'll get rid of the revolutions. So now, if we just do that, we'll have radians per minute. We want radians per second. So let's get rid of the minutes and keep seconds. 60 seconds in 1 minute, right? That'll get rid of our minutes, and then we'll have radians per second left over. So let's see what we get. 80 times 2 pi divided by 60 is 8 pi over 3 radians per second. So that's approximately That's approximately 8. Let's go 2 6 figures. So we'll say 8.4. Okay. Now part B says find the linear speed of the belt in centimeters per second. Okay. Well, so for this, so I'm just picturing a pulley with like a belt on it, right? Something like that. So we want to know how quickly the belt is moving. Well, when the belt is on the pulley, it's a circular arc, right? And we know that the linear speed is related to the angular speed via this relationship, right? V equals R times omega. where r is the radius. Now we're told that the pulley, a belt runs a pulley of 6 centimeters. I think we're meant to assume that that's the radius. Right? So the linear speed would be 6 centimeters times 8 pi over 3 radians per second. This is going to leave us with a velocity in centimeters per second. Let's see. 8 pi over 3 times 6 is 16 pi. So it's 16 pi centimeters per second. That's approximately 50.3 centimeters per second. Okay, so that's how fast the belt is moving. Okay, so I think you kind of get the idea. Probably we'll look at one more example. It says a satellite in a circular orbit 1,600 kilometers above the surface of Earth takes 2 hours to make an orbit. The radius of Earth is approximately 6,400 kilometers. Part A says approximate the linear speed of the satellite in kilometers per hour. The linear speed. Okay, so the linear speed, again, this is r times omega. So, but in order for this to work, we need omega to be in radians. We need for theta to be in radians. So we need omega to be in radians per. In this case, we want the speed of the satellite in kilometers per hour. So we want omega to be in radians per hour. Okay. Now what do we have? What were we given for omega? We were told that it takes the satellite 2 hours to make an orbit. So it goes one complete orbit in 2 hours. So that's half an orbit per hour, right? We actually want to keep hours, but we want to get rid of orbit. We want to change orbit for radians. So how many radians are in one orbit? Well, 2 pi, right? That's just one rotation, one revolution, right? That'll get rid of the orbits. So 2 pi radians in 2 hours, well, that means pi radians per hour. Okay, good. Now what about the radius? It says the radius of Earth is approximately 6,400 kilometers, so that's taken care of. So we're ready to plug stuff in. We can say this is 6,400 kilometers times pi radians per hour. So that's going to be 6,400 pi kilometers per hour. How much is that approximately? So, well, that's really fast. 20,106 kilometers per hour. I guess if we were doing sig figs, it seems like we've got 4 significant figures, so 1, 2, 3, 4. So I should really just round this up so that I've rounded to 4 sig figs. Anyway, 20,110 kilometers per hour. That's interesting. That's fast. Oh, no. I've led you astray. Hold on, because the satellite is in a circular orbit 1,600 kilometers above the surface of the Earth, and the radius of the Earth is 6,400. So really what we have is this situation. I apologize. What we have is the satellite is orbiting out here. This is 6,400, and then this is another 16. So really the radius is 6,400 plus 16. So that's 8,000. So that should actually be 8,000 pi, right? So 8,000 pi. Ooh, that's even faster. Yeah, okay. So 8,000 pi is approximately, again rounding to 4 sig figs, we would say 25,130 kilometers per second. Anyway, so there we go. Okay, so now part B. It says approximate the distance the satellite travels in 4.5 hours. Okay, so the distance that it travels in 4.5 hours. Well, the distance that it travels, since it's traveling on a circular path, it's going to be an arc length s, and that's going to be r times theta. Now r, again, we already have, r is 8,000, right? It's the 6,400 plus the 1,600, so it should be, so r should be 8,000. But theta, well, we're going to have to figure out what theta is. So we know that omega equals theta over t, so that theta is omega times t. Omega we found in the previous problem, that was pi radians per hour. So this is pi radians per hour times t, 4.5 hours. So the hours are going to cancel and leave us with radians, which is exactly what we want. But that's 4.5 pi so 9 pi over 2, right? Okay, so theta is 9 pi over 2. We're ready to plug stuff in. So we can say, alright, so the distance traveled s is r, which we said was 8,000 kilometers, times theta. That's 9 pi over 2 radians. And remember, radians are just real numbers, so you don't even need to write the unit. But kilometers times radians is just going to be radians, right? Anyway, 8,000 times 9 pi over 2 is 36,000 pi kilometers. So that's approximately, well, to 4 sig figs, we'll say, is 113,100 kilometers. That's rounding to 4 sig figs. So it's 113,100 kilometers. So that's pretty far in just 4.5 hours. But anyway, but there you go. That's it for angular and linear speed.